really that far to carry it in the first place. Yeah.
And then also for like yesterday for the RNA polymerase to go in, what like the DNA, the two strands like not helicase, like because it could be in the middle of
The RNA Let's get started. Okay, so we're going to talk about translation today. This is going to be finishing the story that we started last week where we were talking about all of these different types of RNA and everyone was very confused. We're going to finally finish the story so that hopefully it comes together now. This idea of translation is the last part of the central dogma where we're going to go from RNA to protein. So the mRNA is our blueprint. This is what we've made from the DNA, and now we can use it to code for amino acids. But we're going to do it in codons, meaning that we're going to take 3 bases, and those are going to code for a specific amino acid. So you'll have 3 bases out of your 4 put together, and that codes for a specific amino acid. We will not ask you to know them all. There's 64 potential codons that can make 20 different proteins, or 20 different amino acids, I mean. And the only one we want you to know is the start codon. Okay, so I'm going to say, know this one. The start codon is your initiation that tells you where to start your translation. That is going to be an AUG base codon, and it will code for a protein called methionine, which I will abbreviate as MET. You're also going to have a stop codon that's going to tell you when to terminate this translation. Your stop codons can be 3 different codons. You don't have to memorize these, but if you're, you love these details, the easiest way to remember this is you are annoying, you go away, you are gone, okay? That's your stop codons. Now we can talk more about the tRNA. We said that the tRNA had a complex 3D shape. It's not a ribozyme, it doesn't catalyze, but that 3D shape will make it possible for it to actually do its job of shuttling these amino acids to the ribosome to make a protein. This is going to have an anticodon on it. An anticodon is just complementary bases to particular codons. So each tRNA has a specific anticodon that can match a specific codon that codes for a specific amino acid. So it's all very, very specific. In order to get that amino acid onto the tRNA, you're going to use an amino acyl transferase. That's another protein, and we'll show how exactly it is putting that amino acid onto the tRNA so that the tRNA can then do its job. And then we'll talk again about the ribosomes. So up until now, we've just been like, hey, ribosome, blob. It's really 2 different subunits, a large ribosomal subunit and a small ribosomal subunit. The small ribosomal subunit is the one that's going to read the mRNA. It will scan for that start codon, and when it does, it will bring in the large ribosomal subunit. You'll put those together as a ribosome. And then it's your large subunit that can be the tRNA binding site, so the tRNA can bring those amino acids in. And then it will catalyze peptide bonds between the amino acids that have been brought in by the tRNAs. Right. Then we'll put it all together. I'll try to draw you pictures. We know that's, I'll try. And then we'll also show you prettier pictures. And there's a video under Tools for Success on the Canvas page. It shows the process of the protein translation at the ER. So it's really going to be helpful for you to see that in terms of transmembrane. Because even if I was a great drawer, that's still something that's very difficult to draw out and show you in 2D form. But this is also going to give you just a better idea of how the tRNAs are coming in to drop off the amino acids and how those bonds form and the protein is made. So for a cytoplasmic protein, just meaning any protein that we leave in the cell, this is going to be done on the free ribosomes in the cytoplasm. But if it's secreted lysosomal or transmembrane, we have to take that to the ER. And we said there was a signal for that told it that this needs to be taken to the ER. That's a signal peptide. It's on the protein itself that's being made. So the protein self-identifies and says, I shouldn't be here. A signal recognition particle says, ooh, I see you. You don't belong here. Let's move you to someplace better. Takes it to the ER. And then it's going to come into contact with the translocon, which is a pore in the endoplasmic reticulum that will be the point where you're feeding the protein through into the lumen of the endoplasmic reticulum. If you're going to be doing a transmembrane protein where you're not just feeding this protein into the lumen and letting it go, but it actually has to be threaded through the membrane itself, you have to have start and stop transferases. These are going to be kind of like signal peptides, but they're going to be signals that these have to stay in the membrane. And so we'll walk through that a few times. Okay, but starting with our mRNA, we know that mRNA is that blueprint. It was made from DNA. Okay, this is going to code for the amino acids in your protein. So we have a strand of mRNA. Just to reiterate this, we always read DNA as 3 to 5. We synthesize RNA 5 to 3 because we're making it complementary and anti-parallel to the DNA it's reading. When we read mRNA to find the codes for the amino acids, we're going to read that 5-3. Okay. So we've got our strand of RNA. I'm going to put some bases in here. Let's say that's C, C, A, U, G, G, A, G, U, G, G, A, C, C. You guys want to look up what ACC is for me back there, since I forgot it? What amino acid is coded for ACC, please? UGA. Okay. So we are going to read this in sets of 3 as codons. Codon is 3 base sets. And we have to do this way because we only have the 4 different bases in mRNA, our cytosine, guanine, adenine, and thymine, uracil in RNA. If we used each base to code for an amino acid, we'd be limited to 4 amino acids, but we have 20 that we need to be coding for. Even if we tried to do this in pairs and said, okay, we're going to use 2 of these bases to make a code, we'd only get 16 possibilities. So that's why we have to do it in these 3 base sets. But that actually now gives us 64 different codons that we can have. And we only need 20 proteins. So as it turns out, not all codons will code for a protein. Our stop codons do not. Where are my stop codons? Here. There are no amino acids that match these particular codons. Other codons will have multiple different codons that code for the same amino acid. And again, you guys don't have to know those except for the start codon and the methionine. When you are looking for your start codon, that's an AUG. And that's your site of initiation. Okay. We said that this is going to code for the protein methionine. And then we have our stop codons, which terminate. Okay, so now that we have to read this in 3 bases in these codons, it becomes really important where exactly we've started. Because if we start at the wrong spot, instead of reading AUG, and then GAG, then UGG, ACC, and UGA. If you start at this A instead, you're going to read AAU. You'd end up reading AAU, GGA, GUG, GAC. That's going to be completely different amino acids that get pulled in. So that would make a totally different protein, which wouldn't function the way it's supposed to. So this idea that we have to have this start codon, and that's where we need to start our translation, this is the open reading frame. And it's set by that start codon. I'm going to erase this because I'm going to write in the names of the amino acids. Not because you need to know them, but just because I'm going to use them as examples. So GAG is going to be glutamate. UGG is tryptophan. ACC is threonine. Is that THR? And then UGA is a stop codon. Okay, so again, that's a really, really short mRNA. That's only 4 proteins total that we made here. Sorry, 4 amino acids in this protein. So I don't think there is a protein that's actually that small. Most proteins are thousands, if not hundreds of thousands of amino acids long. But for the example, that's what we're going to use. So how do we actually get to the amino acid that we're coding for? We start with a tRNA. And a tRNA is going to have this complex 3D structure that includes 3 of these hairpin loops that we talked about, and then a stem. You don't have to memorize the structure of the tRNA either. I just want to show you how it works. I'll also tell you that this is a fairly decent representation of what it looks like in a 2D form. This is not, we're just making up some shape to show you. That's actually kind of what it looks like. However, I'm not going to draw it out like that every time I draw a tRNA. So this is how I draw my tRNAs. There's your hairpin loops, there's your stem. What's important about this shape for us is that this bottom hairpin loop is going to have 3 bases on it. And these are anti-codons. So each tRNA has a specific anti-codon that's built into it. And that anti-codon is complementary to the codons. So if this tRNA was meant to pair with your start codon here, it would need complementary bases. So AUG would be UAC. And this stem up here is where it's going to hold the amino acid. In this case, AUG is coding for methionine. So this is going to be a methionine amino acid that gets carried on this particular tRNA. It will always carry methionine. That's the only thing it can carry because that's what it's coded for. Now we'll walk through protein synthesis and I'll show you exactly how this is happening. But what this is going to do is it's going to shuttle this to the ribosome and drop off this amino acid. When it does that, you end up with an empty tRNA. We reuse these. So we have to recharge them. We have to put another amino acid back on it so that it can do its job again. And doing that requires another protein called an amino acyl transferase. Okay, so like the name suggests, this is going to help transfer an amino acid to the tRNA. Now, just like these tRNAs are very specific, they only match a certain codon, they only carry a certain protein, they're also going to have very specific 3D shapes that will differ per tRNA. They will match very specific amino acid transferases. So if this amino acid transferase can come in and bind to this, then the 3D shapes are perfectly fit. And let's say that this guy is carrying CUC. Okay, so that's the anticodon for this tRNA. That means that this is going to be carrying a glutamate, or should be carrying a glutamate. So this amino acid transferase is going to be transferring this glutamate onto the tRNA. Now the tRNA can shuttle that back to the ribosome, drop it off, and it'll just go back into the cytoplasm, find another amino acid transferase, pick up another amino acid, and just keep going through that cycle. Okay. The last thing we should talk about is the ribosomes. So this is rRNA. So again, instead of just being a blob, it's actually two subunits, which are going to look like two blobs. This is your small ribosomal subunit. And this is your large. This guy reads the mRNA, this one catalyzes the peptide bonds between the amino acids that are brought in from the tRNA. Okay, if you've had any genetics before, you know that this large ribosomal subunit is actually going to have 3 binding sites for the tRNAs. They have to go through a whole series. We don't get into that level of detail. I'm not going to talk about the 3 different binding sites or exactly what moves them from one to another. We're just going to say the tRNA can bind here and that it will release the peptides it's holding, the amino acids that it's holding, and that the large ribosomal subunit will then catalyze the peptide bond between them. All right, so let's look at that unless anyone has questions before. Great, let's take a look. So you had your nucleus. You made this RNA. You edited it. And then once it was final, it was able to leave through the nuclear pore. And now this mRNA is out in the cytoplasm. Your ribosomes, at rest, when they're not translating, are separate. 2 separate subunits that just float around individually. The small ribosomal subunit will come in and pick this up. I'm going to draw it bigger here. So there's mRNA. Your small ribosomal subunit comes in, finds the AUG start codon. That's going to cause it to recruit the large ribosomal subunit. That doesn't look very large. Okay. Once that happens, now you can start bringing the tRNAs in to bind in this large ribosomal subunit. You'll have your tRNAs out here in the cytoplasm. They're going to be checking out this as the ribosome moves down and see if its anticodon can actually bind to the codon that's being read at the moment. In this case, the only one that's actually going to be able to bind is one that carries the anticodon of, come here, UAC, complementary to that start codon. And so that's going to be carrying on it this methionine. Okay, we said the next set of bases on our example here were GAG. So the next tRNA that's going to be able to come in and bind is going to have an anticodon of CUC. And that's going to be carrying a glutamate. Keep in mind that these are bases. They're still nucleic acids. And when they're complementary like this, they can hydrogen bond. So that's how the tRNA comes in and attaches. When it does that, the large ribosomal subunit can then create this peptide bond between them. So this was glutamate. When these get bonded, peptide bonds between these amino acids, the tRNAs can release them. Okay, so the tRNases will drop those amino acids. They're now becoming part of the protein that's being made, and the tRNAs can leave. So now you have your empty tRNAs out here again. They will then get an amino acid transferase to put another amino acid on them. And then they'll come back and see, can they find another codon that they complementary bind with? In this case, this first guy with the UAC on him, he's done for this protein. We don't have any more AUGs in that. So he won't get used again. Neither will our glutamate carrier, CUC. Probably would have normally, but with my little truncated 4 amino acid protein, it doesn't get used again. So we're looking now for our next guy. And again, like I said, there are actually 3 spots in here. I just didn't draw that. But once you've read this section, you will move the entire ribosome, small and large subunit, down. And then you'll be reading this next base set, which was UGG. So you want a tRNA to come in. That has a ACC on it. Oh, that's interesting. So this is tryptophan. Once this comes in and hydrogen bonds, we can create this peptide bond between the 2 amino acids. This tRNA will drop it, and so on all the way down. Just keeps reading each codon, adding the new amino acid, creating the peptide bond between it, and then we have a final protein, which we usually just draw as a squiggle. We're like, okay, we released it. There's our protein. And remember that the reason we could release this is because we got all the way down to a UGA, which was a stop codon. This does not have an amino acid that can match it. So there's nothing to add. That's the signal to terminate. Your small and large ribosomal subunit will separate. Okay, so this causes disassembly. of the ribosome and release of the last portion of the protein. So again, then we would have our final protein. What we've made here is the primary structure. We just pop bead to pop bead each amino acid, and then when it gets released, it can start, well, it'll probably start even before as it's feeding, but it can start doing the secondary structures and then its final 3D structure. All right. Questions on this? Yes?
Does the tRNA have to be in the large ribosomal subunit, or can it go by itself?
So the question is, does the tRNA have to be in this large ribosomal subunit? Yes, there are actual binding sites that they have to fit into.
So do they enter into the large subunit, or are they only there? Because it looks like they're leaving.
So they are going to come, the tRNAs will enter the large ribosomal subunit if it can find its matching codon. If it can, it just moves on. If it finds it, it binds and it stays in its binding site in the large ribosomal subunit until it releases its protein, its amino acid, and then it will get kicked out of that binding site. Essentially what's going to happen is this whole thing will move, and then the tRNA will be out in the cytoplasm again with nothing on it. Yeah. No questions. Wow. Okay.
So if this amino acid is going to join a cytoplasmic protein, are we talking about free ribosomes right now?
So the question is, if this is a cytoplasmic protein, are we talking about free ribosomes? Yes, absolutely. Okay, remember too that we said that all ribosomes start as free ribosomes. So we can walk through this process again for the transmembrane secreted and lysosomal. You guys ready for that? All right, let's give it a try. Transmembrane, lysosomal, and secreted. You send your edited mRNA out. You know, I know we said we read 5 to 3, but I didn't point it out here. This would have to be your 5' end. This is your 3' end. This ribosome will move towards the 3' as it reads. Okay, just to be clear. So we're in the cytoplasm. A small ribosomal subunit will join, pick up this mRNA and start reading it. It'll find that AUG start code. It will bring in that large ribosomal subunit, and it will start the protein synthesis process. I won't show all the tRNAs here. I'll just show that we're making this protein now, and as you make it, it feeds out. Okay. If we have our first 17 to 30 amino acids in this growing protein as hydrophobic amino acids, then it's a signal peptide. Okay, so again, this is built into the protein itself. You start making this protein and you make a whole bunch of these hydrophobic amino acids, and they're in the cytoplasm. They don't like this. They're not very happy being here. So we have this other protein. Called a signal recognition particle. The signal recognition particle will have hydrophilic R groups on the outside so that it's quite comfortable in the cytoplasm, but it will have a binding pocket inside that has hydrophobic R groups. So you could think of it kind of like a hot dog bun. Normally it's closed, so it's keeping itself secure, but if it finds a signal peptide, it will bind around it so that the hydrophobic amino acids and the hydrophobic portion of that signal recognition particle can stick together and stay out of the plasm. So I know I can't draw it that way, I just can't, but you can imagine that this is now wrapped around that signal peptide to protect it. This signal peptide now acts like a tugboat. So now this is going to drag this entire complex to the ER. This will stop translation. And moves complex to the ER. All right. Do you guys have that written down? Because I'm going to have to go to another board and it's going to be hidden. We're good? Okay. So here is our endoplasmic reticulum. This side down here is the lumen of the ER. So that's inside the membrane. This portion up here will be the cytoplasm. You'll have a transmembrane protein in here called an SRP receptor. So let's redraw our small and large ribosomal subunits reading an mRNA, starts making a protein, but it has this hydrophobic portion to it. That got picked up by that signal recognition particle. So this was the signal peptide. And this again was the SRP, or signal recognition particle. So this is going to drag all of it. It's going to hold on to the signal peptide. That's still attached to the protein that's being made by the ribosome. The small and large ribosomal subunits are connected, sandwiching that mRNA. So the whole thing will get dragged down to the endoplasmic reticulum, and your SRP will bind to the SRP receptor, holding on to the signal peptide. That is still attached to the rest of the protein coming from the ribosome. Okay. Now I know there's a lot of proteins here. Sorry to do this, but I've got to add one more. Actually, I'm going to have to add at least two more, but now we're going to talk about this. It's a transmembrane protein called a translocon. Despite my drawing, this is a pore. This is what we said was the hole in the endoplasmic reticulum. This is what you're going to feed your protein through as you're making it. By bringing this entire complex closer and binding to the SRP receptor, the ribosome is now close enough to that translocon that it can bind. When it does that, so this just shifted this way, this signal peptide will get released from the SRP. Okay, so now we've just got our protein with our signal peptide on it. And that's going to start feeding into the translocon. So I'm going to redraw this here. Here's our translocon. Here's our ribosome. As we feed this through, something kind of strange is going to happen. So in the beginning of the semester, we told you that if we had a transmembrane protein, that the outside portion of that transmembrane protein that was in contact with the fatty acid tails of that membrane would have hydrophobic R groups on it, and that anything that was facing towards the inside of a channel would be hydrophilic, because why else would you have a channel? This is an exception to the rule, the only one we will talk about. This is actually going to have hydrophobic R groups facing the channel. Meaning that your translocon can bind to a hydrophobic portion of a protein. So when you try to feed this protein through the translocon, that signal peptide is going to stick. But the rest of this protein can feed right through. So you're making your protein, and as you make it, it's going to feed. It's connected to the signal peptide that is now connected to the translocon. Okay. You guys with me so far? No, I'm seeing a lot of head shakes. Ask questions. I'll redraw it if I need to. What's going on?
What's a translocon?
What's a translocon? Okay, perfect. So this is a translocon. A translocon, oh, that's terrible. A translocon is a transmembrane protein in transmembrane in the ER membrane. This is where you're going to feed any of your membrane-bound proteins through. So any of your transmembrane, lysosomal, or secreted proteins will feed through this to get to the lumen of the ER. Okay, so this was your ER lumen here. Your translocon was just that transmembrane protein that created a pore into that membrane so that you can push your protein in. Yeah?
Can you redraw this process just one more time?
Which one? This whole thing?
Yes, please.
Absolutely. Do you want to start with bringing it in on the SRP? We could do that. I'm going to erase this. So here's your ER membrane. Here is our SRP receptor. We had a signal recognition particle that picked up that signal peptide that was being made from a ribosome, and it's going to drag the whole thing here. So this binds to the signal recognition particle. Remember that this is like our hot dog bun. This is what was able to pick up that signal peptide and keep it safe. It's attached to that signal peptide, which was 17 to 30 amino acids. And that's going to be attached to the rest of the protein it's making coming out of a ribosome. Okay. Once this attaches the signal recognition particle to the SRP receptor, it's going to basically pull this whole thing close enough to the ER membrane that the ribosome can bind to a translocon. So this is step one, binding of the SRP to the SRP receptor. That's going to swing this ribosome down. So now it can contact this translocon. And once the ribosome is bound to this translocon, it will release from the SRP and receptor. Okay, so this would now be free. But we've shifted it over here. So really it's looking like this. You'll continue with your protein synthesis, and it's going to start pushing it into this pore, into the lumen of your ER. But because you've got these hydrophobic R groups inside the translocon, the hydrophobic signal peptide will stick. So this is like that signal peptide. So now you've got this portion of it stuck, but you can still push the rest of it through. As you continue synthesis and you keep pushing out more and more protein, this will just elongate. Okay? You just keep making it here, it keeps pushing it in, it just elongates. Eventually, you're going to reach that stop codon. So we'll just say it hit a stop codon here. That's going to cause your ribosome to dissociate. It will release the mRNA and it will release this protein. When it releases this, it's just going to end up completely here. Okay. Go ahead.
For proteins that are through multiple times at multiple passes, is each portion that is inside of the membrane going to be hydrophobic as well?
Yes, but we're getting a little ahead. So the question was about transmembrane proteins, which we haven't actually shown yet. This, which we've pushed completely into the lumen, has to be either a lysosomal or a secreted. Lysosomal. Holy crap. Lysosomal or secreted. The last step that we have here is to cut off this signal peptide. That signal peptide was just a signal to move this here. Once we're done with it, we cleave it. So we're going to have yet another protein. This is a signal peptidase. And that just means it cuts off that signal peptide. So once you've cut that signal peptide, you can release the entire protein. And because it is now released and free, it can form its full shape, so it'll, do whatever it's going to do. There's your protein in the lumen of the ER. We still have to glycosylate it and move it to the Golgi and everything else we talked about, but that's how we're going to make those lysosomal and secreted proteins. Yes?
So this used to be a free ribosome.
This used to be a free ribosome, yes. They all start as free ribosomes.
So then now it becomes a bound ribosome?
Once it's bound to this translocon, we now consider this to be a membrane-bound ribosome. Once it's finished with translation here, and it disconnects and releases the mRNA, it goes back to being a free ribosome. And it will hang out in the cytoplasm and wait for the next piece of mRNA and start reading it. And if it's cytoplasmic, it'll stay and it will make it. If it's not and it has a signal peptide, it'll get dragged back to the ER again, attach, make the protein. When it's done, release again. So this is the same ribosome, free and membrane bound, or just where it's actually synthesizing, in the cytoplasm or on the ER membrane.
Is this occurring on the smooth ER or the rough ER?
So the question is, where on the ER? Smooth or rough? It's always going to be rough endoplasmic reticulum with our ribosomes, because that's the roughness is the studying of those ribosomes. Smooth endoplasmic reticulum just makes lipids. We don't really talk about lipid except when we talked about, glycerol and fatty acid tails. That's about the extent of lipids in this class. Yes?
So the translocon is a protein, right?
The translocon is a protein. It's a transmembrane protein.
Okay, so it's made the same way?
Yes. So this translocon, because it was transmembrane protein, had to have been made through this process of being brought to the ER. It just stayed there. Yep. Anything else? Yes.
So after the signal peptide bonds like stuck to the translocon, is that the protein gets pushed over to the lumen?
So when we cut off this signal peptide here with the signal peptidase, yes, then this portion just kind of falls in, and the entire protein is now in the lumen of the ER. Yeah. Yes.
Are any of these like the start and stop transferase? Is that like?
We have only covered secreted and lysosomal. I can't get to transmembrane today. I'm not even going to start. So everything below this, well, no, actually, the start and stop transfer we have not covered yet. This will be Monday. Yes.
Can you go back to the board that has the translocon feature?
I'm guessing it was the one behind this. This one? Okay. Like I said, I think this is probably a good place to stop. Please try to watch that video if you can this weekend. It'll help you on Monday, and have a great weekend.
So